In question 1, we want to sort the following unordered list using the various sorts we've learned about in lecture. So the first sort we'll use is insertion sort. And in insertion sort, for every element we iterate over, we swap it left until it's larger than the elements to its left. If we define an inversion to be the swap of a pair of elements, then the best case runtime of this algorithm is theta n plus k, where n is the number of elements in the list and k is the number of total inversions. The worst case runtime would be theta n squared. So going back to our list, we begin by looking at 0. There are no elements to the left of it, so it is in its rightful place. Next we look at 4. It is greater than 0, so we don't need to swap. Okay, next we look at 2. It is currently not greater than all of the elements to the left of it, so we swap until it is between 0 and 4. Next we look at 7. It is currently greater than all of the elements to the left of it, so it's in the right place. Next we look at 6. We need to swap it with 7 to sort to the left. The next element to look at is 1. We need to swap until it is between 0 and 2. Okay, the next element to look at is 7. No swaps are needed. And next we look at 3 and swap until it is between 2 and 4. And last we look at 5 and swap until it is between 4 and 6. And this is our sorted list. Next, we'll try to sort the same list with selection sort, in which we repeatedly find the smallest element and put it in the front. At each iteration, we can consider everything to the left of the element we are looking at to be sorted. And the best case and worst case runtimes are the same, and that's just theta n squared. So first we look at 0. None of the elements are smaller, so we don't change anything. We see that 1 is the next smallest element in the unsorted portion of the list, so we swap it with 4. Okay, 2 is the smallest in the unsorted portion now, so we don't need to modify anything. Next we see that 3 is the minimum of the unsorted portion, so we swap it with 7. Next we see that 4 is the smallest, so we swap it with 6. Okay, 5 is the next smallest, so we swap it with 6. 6 is the next smallest, so we swap it with 7. And at this point there is nothing left to sort, so we are done. Next we'll take a look at merge sort, in which we recursively sort the halves of the array. If there is only one element in the list, we return the single element. Otherwise, we cut the items of the list into 2 halves, recursively sort them, merge the sorted halves, and then return. The best and worst case runtime is theta n log n. So we begin by splitting the list into 2 and making recursive calls on them. In each of the 2 calls, the lists are halved again and recursed upon. And in those recursive calls, the lists are split into lists with only one element. So when those lists are recursed upon, the only element in each list will be returned and sorted by the call frames that initiated the function calls. So 0 and 4 will be merged back into a list of length 2, and the same will happen for 2 and 7. And then 1 and 6 will be merged into a list, and the same goes for 3 and 5. And working our way back up, the 2 lists on each side will merge into lists of length 4. And finally, we want to merge the 2 lists of length 4 into one sorted list of length 8. And we are done. The last sort we'll use is heap sort, in which we place everything into a max heap pop off the max element and place it in the back of the array. Note that we have to heapify the array initially and also reheapify after every deletion of the max element. The best case runtime is theta n, which occurs when all elements are the same, so you don't need to heapify. The worst case runtime is n log n, which comes from the first heapify as well as the heapifications after each deletion. First, we place all of our elements into a max heap and heapify. And we see that the maximum is 7, so we pop it off and place it in the back of our list. We also reheapify the heap and see that the next maximum is 6. So we pop off 6 from the heap and add it to the back of the list and reheapify once again. So the maximum is now 4. We pop that off from the heap and place it in the back of the list. And now the maximum is 2. We pop it off and we're left with 0. And now we're done.